Video number 2, and this is dealing with making dilutions. So dilutions are any time when I give you or you have a solution that is a little too concentrated and you need to make it less concentrated. So this is the equation you use. You have M1V1 equals M2V2, and it's a really nice equation. It's very useful in chemistry. Sometimes the ones we give you, some equations, you may only use in one situation, but this is really applicable to a lot of lab situations. So what you have is for the molarity you want times the volume you want. So this is of the dilution. It's going to equal the molarity you have, like the one that's too concentrated, times the volume you want. So you just want to make sure that your volumes are in the same units, and obviously your molarities are in molarities. So if you look at our two examples here, we have how many milliliters of aqueous 2 molar magnesium sulfate solution must be diluted with water to prepare 100 mils of aqueous 0.4 molar magnesium sulfate. So this is what we want. We want 100 mils of 0.4 molar, and you can see I put them right in here. And what's nice about this equation is you can be in milliliters or you can be in liters. If you remember with molarity, you have, like when you're doing a formal molarity calculation, it has to be in liters. But this one, you're just, whatever your unit for volume is, that's what your answer in volume is going to be. But you can see what we want here is the M1 and the V1, and then the stock solution, the one that we have right now, is over here, the M2. So what you do is you multiply the 2 on the left, you divide the 1 on the right here, and what this X is the volume that you're going to need. So what you're going to do is you're going to take 20 mils of that stock solution, and you're going to add water until you reach a final volume of exactly 100 mils. So as easy as that, very nice, very simple equation. Letter C down here, how would you prepare 250 mils of the 0.2 molar salt solution using only a solution of 1 molar salt and water? So same thing, what you want goes on the left here, so 0.20 molarity, and we want 250 mils of it, and it's going to equal the stock solution, which is 1 mil, times our X. So we solve for X, and basically we're going to get 50 mils of the salt solution that we have and dilute it up to 250 mils for the total volume. So it's a nice solution. We're going to be using it in lab once, like right after this chapter is over with our spec lab. Last thing with solutions, and these you just have to be aware that they exist, is colligative properties. So colligative properties is a property that depends solely upon the number of solute, that should say particles, I apologize, let me fix that. There we go. And not upon their identity. So a lot of things with chemistry depend on the chemical, but colligative properties actually don't. One thing you want to know, they have to be what's called if it likes me, volatile, and that just means that they do not become a gas easily. So when you have these solutions, you have to have a non-volatile thing added in. But the major colligative properties we're going to look at are vapor pressure, boiling point elevation, and freezing point depression. So it's basically what happens in all of these situations is the solvent molecules, which we're typically looking at water, is attracted to the solute molecules. And what happens is the liquid phase stays longer. So what you'll notice is the boiling point goes up, the freezing point goes down, and there's just less vapor pressure overall. So the liquid phase is basically extended in all directions because of this interaction, which is a pretty cool thing. This is why you put salt on your sidewalks in the winter, because what happens is the salt interacts with the ice, it lowers the freezing point, and then what happens is your ice melts. So that's kind of a nice little connector. So these are just some cool things here. You can see here this is normal water, and you can see it has a certain amount of atmospheric pressure, the vapor pressure here. You can see when we have a solution, though, that there is lower vapor pressure, and it's because there's these attractions between these molecules that were, not there before, and there's just not as many of the atoms or molecules are becoming a vapor. And you can see on our graph over here, you can see the vapor pressure is this pink line right here where I'm going over my cursor, and you can see the solution, it's definitely at a lower point comparatively. So vapor pressure with colligative properties decreases. Boiling point, you can see the boiling point here. So the boiling point, we're doing it at 1 atmosphere, so like normal everyday temperature. You can see here on the pink part of the graph, that's normal boiling point for like just the solvent. And you can see this is over here, the boiling point for the solution. So the boiling point goes up, And again, you can see same kind of graphic here. If you just have the chemical, you can see that it's boiling at, whatever rate it's going to boil at. When you have these strong interactions between the solute and the solvent, you can see that there's less atoms or molecules leaving the solution, so it takes a longer time for your boiling point to occur. So your boiling point also increases. And last but not least, we have our graphical representation of the freezing point depression. So it's down here now on that graph, but you can see here, this is normal freezing point, and you can see that the blue one over here, it decreased, and we have a new freezing point here. This picture over here just shows you what solutions can do. So rain is just normal water. I mean, it has a little bit of dissolved into it, but not much. And you can see that obviously it was a freezing rain, severe freezing rain, and obviously, very severely froze. But you can see in the background, you have the ocean, which is highly, has a lot of things dissolved in it, and at the same temperature, it didn't freeze. So you can just see the effect that having a solution or not having a solution can affect how things behave. And the last slide for this one is just these two cool examples of this one. What you can think of it from another perspective is when you're freezing things, for example, like when you're going from a liquid to a solid, you're getting more order into the system. And for example, when you make a mixture, what you're doing is you're adding more chaos. So it's harder for the liquid to get around the molecules and escape. It's harder for the liquid to form a crystal and freeze. But these are just two real world examples here. You have an example of this too in your body, but like if you think about it, we contain a lot of water. So realistically, how do some animals actually survive in these really harsh environments? What kind of mixture is in their body that allows that to do this? And they actually say some frogs almost have like an antifreeze mixture in their blood, in their circulatory system to prevent them from dying. So even though they're clearly frozen, how are they still able to survive? And the same thing happens with plants. I mean, plants have to protect themselves. Most plants, the plants that don't have any protection, that when it frosts, they die. And some plants have protection that they can actually do this. And in all these cases, it's due to colligative properties, which is pretty cool. That's it.